Hello students, welcome back to ME515 Finite Elements Methods in Engineering. It's your instructor Dr. Jitendra Prasad. Before we went on leave, we were studying three-noded triangular element. A triangular element, three-noded triangular element is shown here. Its vertices are numbered as 1, 2, 3 and each of the vertices has one node. Node 1 has coordinates x1, y1, node 2 has coordinates x2, y2 and node 3 has x3, y3. Then there is a point P inside the triangle. The coordinates of point P is xy and this point divides the triangular area A into three parts, A1, A2, A3 as shown in this figure. So obviously A equal to A1 plus A2 plus A3. We found out, we derived in our class that the shape functions, there will be three shape functions and shape function 1 N1 is given by area A1 divided by area of the whole triangle. Similarly, N2 equal to A2 divided by A and N3 is equal to A3 divided by A. Now the trial function, we know that Txy is equal to summation of the shape functions multiplied by the nodal temperatures Ti. So if T1, T2, T3 are the nodal temperatures, then the temperature field inside the triangular element is given by N1 T1 plus N2 T2 plus N3 T3, where the shape function we already know from the previous slide. Here A is equal to the area of the triangle, which can also be given in terms of the coordinates of the vertices, that is half of determinant of a matrix having 1 x1 y1, 1 x2 y2, 1 x3 y3 as members. A1 is the area of the triangle made by point P and points 2 and 3. Similarly, A2 is the area of the triangle made by points 1, P and 3. A3 is the area of the triangle made by points 1, 2 and P. And do you remember how you got these equations? We had a triangle with the coordinates as shown in the figure, and you first assumed Ni equal to alpha I plus beta I x plus gamma I y, where I equal to 1, 2, 3. Thus there are 3 by 3 equal to 9 unknowns. And you then solve the following equations. Ni xj yj equal to delta ij for I equal to 1, 2, 3 and j equal to 1, 2, 3. Here also total 3 times 3 equal to 9 equations, where delta ij equal to 1 if I equal to j and delta ij equal to 0 otherwise, that is when I is not equal to j. This delta ij is also known as Kronecker delta. Now, is there an easier method where there is no need to solve a system of equation? Okay, so let's look at the alternative derivation of shape function. So we start with the original triangle we had, and n1, that is the shape function, is linear, and you know that it has to be 0 at points 2 and 3. Now the idea is to find a linear function f1 xy whose value is 0 at points 2 and 3. And so if you find that equation, this will look like this one: f1 xy equal to y minus y2 minus ratio of y3 minus y2 and x3 minus x2 and multiplied by x minus x2 and the whole thing equal to 0. You may recognize that f1 xy equal to 0 is nothing but it's actually a line passing through points 2 and 3, and n1 is simply f1 xy divided by value of f1 xy at point x1 y1. Similarly, you can derive n2 and n3. Here also n2 is a line and it has to be 0 as point 3 and 1, and we have to find out a function f2 such that it is 0 at point 3 and 1, and this function has to be linear. If you apply coordinate geometry and find out that function, this function f2 will look like this: y minus y3 minus y1 minus y3 over x1 minus x3 multiplied by x minus x3, the whole thing equal to 0. And again f2 equal to 0 is nothing but a line passing through points 3 and 1, and n2 is simply given by f2 as a function of xy divided by f2 at point x2 y2, so that n2 is equal to 1 at point 2. Similarly, we can find out n3. Again, n3 is a line whose values are 0 at points 1 and 2, and if you find that function f3, it will look like y minus y1 minus y2 minus y1 divided by x2 minus x1 multiplied by x minus x1 and the whole thing equal to 0. Now if 3 equal to 0 is actually a line passing through point 1 and 2, and n3 is simply given by f3 as a function of x and y divided by f3 at point 3, that is f3 x3 y3. So what's next now? We have this test function txy is equal to n1 t1 plus n2 t2 n3 t3, or simply t equal to n1, n2, n3 multiplied by t1, t2, t3 in matrix form, or t equal to n times theta, where n is a vector, n1, n2, n3, and theta is also a vector, t1, t2, t3, and t is the inner product of these vectors n and theta. Now, the weak form for 2D heat conduction equation has gradient of T that we have derived already in the class, and so we need to find out what is the derivative of T. Okay, so we want to find out the gradient of T, which is function of xy. The gradient of T we can write in matrix form. So gradient of T means gradient of n times theta, or which is equal to gradient of n multiplied by theta, and gradient of n we are, or rather we will call it as a B matrix, which may be written as this. Following the conventions we have already followed in the class, or B can be given as a matrix in form of derivative of the shape function. So the members will be del n1 over del x, del n2 over del x, del n3 over del x, del n1 over del y, del n2 over del y, and del n3 over del y, where del n1 del x equal to 1 over twice the area of the triangle multiplied by derivative of the determinant for the matrix 1 xy, 1 x2 y2, 1 x3 y3, which will be equal to y2 minus y3 over 2a. Similarly, we can find out del n1 over del y, which will be equal to half over 2a multiplied by derivative of the determinant of a matrix having 1xy, 1x2 y2, 1x3 y3 as members. So finally the value will be x3 minus x2 divided by 2a. n2 over del x, or the partial derivative of n2 with respect to x, will be given by 1 over 2a multiplied by derivative of the determinant of a matrix having 1x1 y1, 1xy, 1x3 y3 as members, and the value you get is y3 minus y1 divided by 2a. Derivative of n2 with respect to y is given by 1 over 2a multiplied by derivative of derivative of determinant of a matrix having 1x1 y1, 1xy, 1x3 y3 as members, and the derivative is partial derivative with respect to y, and the final value is x1 minus x3 divided by 2a. Now for n3, the partial derivative of n3 with respect to x will similarly be equal to y1 minus y2 divided by 2a, and partial derivative of n3 with respect to y will similarly be equal to x2 minus x1 divided by 2a. So therefore, we can say that B matrix is equal to 1 over 2a, and then a matrix having y2 minus y3, y3 minus y1, y1 minus y2, x3 minus x2, x1 minus x3, x2 minus x1 as members. You will notice that this is nothing but a constant matrix. Okay, so now let's look at the simplest problem. The domain is triangular and gamma is its boundary. The strong form is given by minus divergence of vector q plus s equal to 0, where q is equal to k times gradient of temperature, and the corresponding weak form, which we have derived already in the class, is given by the closed integral of w times q dot n, which has to be integrated over the whole boundary, plus gradient of w dot q integrated over the whole domain, plus w times s integrated over the whole domain. All of the summation is equal to 0 is the weak form. Or we can rewrite the above equation as gradient of w dot q integrated over the whole domain equal to minus w times s integrated over the whole domain plus w q dot n integrated over the whole boundary. Or we can write it as k times gradient of w dot gradient of t integrated over whole domain omega equal to minus w times s integrated over domain omega plus w qn integrated over the whole boundary. Now, if we substitute txy and wxy in the previous equations with these expressions, txy equal to n1 t1 plus n2 t2 plus n3 t3, and similarly wxy equal to n1 w1 plus n2 w2 plus n3 w3, the strong form becomes as follows: k multiplied by integral of gradient of w dot gradient of t integrated over domain omega equal to minus ws integrated over domain omega plus wqn integrated over boundary gamma. This equation can be simplified as w transpose k theta equal to w transpose f, where w equal to vector of w1, w2, w3, theta equal to a vector containing t1, t2, t3, big K is equal to small k and integral of B transpose times B integrated over the whole domain, which will be equal to K times A, here A is area, then B transpose B. Now since B is a constant matrix, F is given by F equal to minus N transpose S integrated over whole domain omega plus N transpose Qn again integrated over the whole boundary. So we finally have W1, W2, W3 as arbitrary variables. So we can get rid of them and we will simply have k theta equal to f. We will now solve problems 8.4 and 8.2 in that order from your textbook in the next lecture video. But before that, please try solving them yourself first. So this video is to be continued. See you in the next lecture video. Bye bye.